introducing you guys to some of the research labs here within the CECS department. But before we dive right in, I'm going to share a little more about the research here at UCF and some of the benefits you guys get from participating within undergraduate research. Thank you. All right, so research here at UCF. UCF being one of the largest public universities in the nation, we attract people from all over the world, all over the country. So it's a huge metropolitan research university. UCF is committed to world-class multidisciplinary research. So there's any field that you're interested in, you could probably find, ranging from STEM to physical sciences to engineering. So there will be something for you if you're interested. We are home to more than 50 centers and institutes. I mean, if you've driven along Research Parkway, you can see all the companies there. They're all doing their labs and trying to, contribute to the advancement of research and engineering and all that. We have award-winning faculty that lead some of these research labs, as well as teach some of the courses that you may be taking or will take in the future. And then we have received more than $200 million in grants, gifts, and sponsored awards. So this is the place if you want to do research. All right, what are some of the benefits about undergraduate research? It's a great way to develop technical skills, get acquainted with all the lab equipment and learning how to use it, and understanding how everything connects and the data it outputs. It's a great way to apply the theoretical knowledge that you learn within your courses, to see the hands-on, data and how it all comes together. It will enhance your problem-solving skills and critical thinking skills. You just see things from different perspectives, find ways to approach it differently, maybe find efficient ways to solve the same thing. You get good practice with writing reports and public speaking. And if you are involved in research, there are opportunities where you can participate in conferences, where you can present your research and share ideas with other fellow researchers. It's a great way to build your network with peers, professors at the university, and researchers in general. This allows you a streamlined path into graduate school if you're interested in your master's or PhD. It kind of gives you a good foundation or basis to go into that. And it just, with all the diverse fields that we have, it allows you to deep dive into the field of your interest. So tonight, like I said before, we will have 6 labs presenting. Our first lab will be with Dr. Parati. He will be doing computational biomechanics lab. This will be followed by Dr. Bhattacharya's lab, but he will be represented by a postdoc student, Dibya, for the experimental fluid mechanics lab. We have Dr. Kaufman, who you guys know is our faculty advisor. He will be talking about the structural dynamics and adaptive structures lab. Then we have Dr. Duval Pereira for U-Space lab. And then Adam Kotler, he is a graduate student. He will be representing propulsion and energy research lab for Dr. Ahmed. And then lastly, we have Dr. El Gahari, who is also our faculty advisor, to discuss the astrodynamics, space, and robotics lab. So, First up, let's welcome to the stage Dr. Parati. Thank you. And here's the clicker. So the white button.
Thank you. Let me see if I can use this. When you guys, I think it's loud, more than enough. Super. So, let me see. Awesome. So thank you for having me, and thank you for giving me the opportunity to present part of the research that we do in my lab. The presentation that I'm going to give is more about on the theoretical side, more on the methodology side. My lab is really like the computational biomechanics lab. And so why I'm here, right? Because we use some of the things that we learn from biology and specifically from viruses to try to design better deployable structures, right? And deployable structure that then we can use, for example, for space exploration. So this work, I started this type of work long ago when I was a postdoc at UCLA, even before thinking about deployable structure. At that time, I was just interested in the maturation of spherical viruses. There are, many different viruses. Some of them are spherical. Basically, we can, lead their shape to an icosahedron, so it looks like a sphere, right? And the things that I was immediately fascinated by this type of virus is that we can look at their structure and try to understand their structure by mapping their structure to a flat hexagonal template. So it's the simplest template, one of the simplest templates we can imagine. It's all made of hexagons. And then we introduce some defects at some specific location. These one are 5-fold defects, right? It's a pentagon cell or a pentamer cell instead of an hexagon. And then we need this defect basically to, when we fold it back up, to introduce some curvature. It's basically what allows us then to go from flat to curve, right? But the bottom line is that we have a very nice way to map a curved shape to a flat hexagonal template. So that was the first reason. And the second thing that we noticed looking at the maturation of this type of virus is that they're all made of hexamers and pentamers, so very like few units, like only 2 in this case. So it's a very modular structure. And the second thing is that during maturation, something happened, right? This one is just one of the phases during maturation. It goes from this type of more spherical shape to a larger shape, which is more kind of icosahedral. And this maturation, there are different explanations why this maturation happened. Without getting into much into details, what we were interested in is looking at the shape change of these units, right? There are these single units and they go from a shear configuration to a more symmetric configuration. And so all the units change their shape, and this change in shape at the singular unit level lead to a change in shape of the global shape changes, right? So then the question came, like, can we actually use this type of modular structure to devise large shape changes as the one that, for example, we would like if we have a deployable structure. We would like to deploy it in one shape, and then we would like to change their shape. And so we start looking into this question and using the same shape and the same type of shape change at the singular cell level. Then we try to use this principle, and then we saw that basically we can change the shape dramatically just by having this modular structure and all the modules changed by the shape in the same way. And these local shape changes, that is translated in a large shape change at the global stage. So that was interesting for us. And of course, so far we were limited to looking at the spherical viruses. And so then the next question came, can we use or can we try to explain maturation of other type of viruses going from spherical to something more complicated? And then we start looking, for example, about these archaeal viruses. They're much larger. The size doesn't really matter. We are in the range of nanometers, but what we want to learn is not about their size. We want to learn about how they change their shape. And they're also fantastic about changing their shape, right? They go from this football-like shape to this to growing very long tails, right? So they're also capable of very dramatic shape changes. And again, can we use the same mechanism that they're using then to change shape of structure that we're actually interested in? So the first question is, can we again construct this type of shapes using a flat hexagonal template? Can we go back to this very simple template and try to come up with the template that corresponds to this type of shape? And so then we went back to the original construction. This construction of the spherical virus is done by, I think I have a pointer, right? This one, maybe no. That's okay. This construction here goes back in 1962, was done by Kasper and Klug. And the idea there again was to introduce this type of defect. So we asked the question, if we want to come up with a construction to do this type of, to represent this type of different type of virus, what type of units do we need? And so then we went really back to Paper's model, as the Kasper and Klug did. This one is a picture from their original paper. They really tried to understand cutting and pasting paper models. And then basically we realized we can still do the same things. We only need to add one basic unit, which is these heptamers. And the reason is because pentamers made of equilateral triangles give you a positive Gauss curvature. You need the heptamer to get a negative Gauss curvature. Great, but we could do that, right? So then we look more into this, we play with Paper's models, and then we come up actually with a more complicated construction, right? But then this more complicated construction that now has some heptamers, we're able to replicate a more complex geometry. So that was encouraging. So far, right, the main things that we learn from viruses, and of course, before I go there, I forgot, and then the second thing is, right, we could reconstruct the shape, but then also we wanted to see if we can mimic the shape changes during the maturation. And again, we use the same concept that we used before, now changing basically the units, the single units material properties, and then we wanted to see if we can grow the tails this way, and every unit is growing slowly, but every unit is basically changing the same way, and now again, it's a simple model, it's a simple problem, but then again, we can use this type of idea to change the global shape of our structure. So then so far, right, what do we learn or what we want to replicate from the viruses, so from what we learn from the viruses? We have a very simple organizational principle, hexamer, pentamers, and heptamers, so allows us to go from positive to zero curvature to negative curvature. We can link it to a flat hexagonal template. We would like to link to a flat hexagonal template, and this is good for manufacturing, is very easy, is good for storage. We can roll it up and store it. And then the ability to achieve very large shape changes using a very simple single mechanism, the same mechanism for all these modular units. So these are basically the things that we would like to mimic, right? When we talk about virus-inspired deployable structure, this is basically what we mean. These are the principle that we would like to mimic because we saw to be so successful for the viruses, right? And really in the next few minutes, I'm only going to talk about the first two of these principles, how we're going to use the first two of these principles. So again, right, for now we were focused on very simple shapes, spherical, this kind of football-like shape. So the first question is, can we extend this to more complicated shapes, still, linking it back to a flat hexagonal template? And we can do that, right? For example, we have looked at a sphere or a sphere with some holes, same things with a torus shape. And again, just as an example, but then you can see like this kind of flower shape where we put holes on this torus. And we can do this tessellation basically using some particle simulations, right? Where we spread particles on this shape, really any shape, and then we equilibrate these particles. And then we can come up with a coverage of the surface, which is just made of these units, hexamers, pentamers, and heptamers, right? So then there is still the hope to go back to a flat hexagonal template, which is just made of these units, and then basically the pentamers and the heptamers are introduced by just placing defects in these templates. So that's good. And then the next things, of course, now that we know we can go back to this flat hexagonal template, and the question is, how do we go back to the flat hexagonal template? So then we want to use these defects, right? These defects to basically decide how we are going to cut up this hexagonal, this tessellation, if you want, and then how we can cut up this tessellation to go back to a flat template. So let me just introduce at least the idea behind that, right? So basically, what we want to do is, first of all, and I'm going to use the icosahedron as an example just because it's simple to visualize. So first of all, we do the tessellation of the surface. We identify the defects, right? Then we identify the defects, and then we connect these defects. And after we have connected these defects, basically we decide that the connection between these defects are going to be the potential cut lines that we are going to use. And these cut lines basically are going to define these unit patches, all divided by these cut lines that we have. So now once we have identified these unit patches, then we need to decide how we are going to unfold them, right? Now we have decided how we cut up this tessellation, right? Using these defects and connecting these defects. So the question is then how we are going to unfold this, right? And we have different choices. For example, again, thinking about very simple example, this one is a tetrahedron structure, and you can imagine the face of this tetrahedron to be your unit patches. And then you can link them, connect them in different ways, right? So for example, if I connect 1 to 3 and 1 to 4 and 4 to 2, then I will get this type of unfolding, which is minimizing the area of the box in which I can print, or if I want fabricate this, manufacture this type of tetrahedron. The same way, I can try to minimize the difference between the width and the height of my box. Can be a design requirement, right? Or I can come up with some other unfolding pattern. So the idea is that we have unit patches, and now we just need to decide how we are going to link together these unit patches. And again, we can try with an icosahedron just to see the same idea, right? We can unfold this icosahedron now to a flat shape, different than the Caspar-Cruke construction that we saw before, by minimizing the area that this flattened template takes on my hexagonal template, right? I can decide to minimize the delta between the bounding box, but I can do something else, right? And for example, I can decide that I want to have a shape like this, and I'll talk about this in a second, in one of the last slides, that this will allow me to get to compact refolding. And we have this in mind because, again, this is a simple example with a surface that is easy to see. When we go to the flat template, we know that at that point, we can always go back to the original shape. We started from there, we unfolded, and now we can go back to that shape. But the question is, how can we store it in the meantime? If we don't want to go back to the original shape directly, how can we store it in the meantime in the most compact space possible, right? And so that's basically having this type of pattern allows us to do. Why that type of pattern? If we think about compact refolding, we want to be able to basically to stack this triangle on top of each other. And we can do that, right? We can do that, for example, where in that case, we just stack two triangles on top of each other. In this case, we stack one triangle on the back and one triangle on the front. What we need to avoid, same things here, what we need to avoid is this type of situation, right? When we have three triangles connected to one. Because in this case, I can fold this one on top of this one on the back, but I will not know where to place this one, right? So then one of the criteria that I want to enforce when I design my unfolding pattern is that all the triangles are only linked by one edge. So we can do that basically, and I'll show you in a second an example. And basically this will allow us to see how to design this unfolding pattern so that then we can store it compactly, right? So just to conclude, hopefully we'll play. Yes, so this one is basically how we can unfold it, right? Nothing special, it's just the one that I showed you before. And then if I want to fold it back, and now not to refold it back to the original shape, but to refold it back, let me see if we will play. Hopefully. Okay, and it takes a second. You can see now what I was just saying a minute ago, when we want to refold it back, and now it's just refold it back to one single triangle. So if we think about storing it, because storing it or for transportation, and then we want to occupy the least space possible, that will be something that we can do. And of course, you know, this is research which is ongoing in my lab. So far, I just show you some very simple cases, and then we would like, of course, with the same principle, right? I show you with an icosahedron, but we would like to extend it to, we are extending actually to more complex surfaces. And then the last slide that I want to show is really to thank the people that are behind everything, the research that I just showed you. Tyler is an undergraduate student that is doing a lot of the 3D printing to actually test and prototype the structure that I just showed you. Wazif is the graduate student that is behind all the movies and the analysis that I show you, and my collaborator, Dr. Tamaran, that worked with me on and with us on developing the mathematics behind this. And thank you for your attention. I'll be happy to take any question now or maybe later. Yeah.
At the end.
At the end, yeah. Thank you.
Thank you.
Oh, yes.
Thank you. All right, so that was the computational biomechanics lab. Next up, we will be introducing Dibya, postdoc for the experimental fluid mechanics lab. All right, here's the mic. Oh, we have it set up. It was Dr. Bush. He sent us All right, we're going to sort out some technical difficulties. For now, we're going to move on with Dr. Kaufman's lab to represent the structural dynamics and adaptive structures lab. Thank you.
Thank you. Sorry about that. Thanks. I was talking to everyone in the back. Good evening. All right. So first, I know there's a Q&A at the end. I'm not going to be able to stick around. I'm kind of in the middle of ferrying kids around. So dropped one kid off at Girl Scouts and need to go pick up some people afterwards. So I'll try to stem off some of your questions maybe. I will get to my research slides, but I want to take a few minutes to talk about undergrad research as an endeavor and help you think about, or help you to think about what questions you might want to ask and maybe answer some of the things you're thinking about now. And so again, I'm Jeff Kaufman. I think you did intros, but I'm one of the faculty advisors of the club. So you may see me from time to time for that as well. I teach aerostructures this semester. Is anyone in that? There we go. I recognize you. Yeah, I was just talking to you back there. And then on the grad side, I teach vibrations adaptive structures. So things very much on the more, even though it's aerospace engineering, more on the aerospace structures side of things, structures and dynamics. So definitely involved in AIAA as well at the national level on technical committees and that sort of thing. But I wanted to talk to you a little bit about my background. When I was an undergrad, I didn't do research right away. It was when I was the summer after my junior year, I did a summer research experience, and it was okay. It was just okay. It was basically studying if we were going to have a mission to, say, Neptune in like 15 years, where would we get the most bang for our buck now in terms of advancing technology until then? So, we've got 15 years till we need to launch. What should we be researching now? What kind, should we be focusing on our imaging suite or our, data communications capabilities? Where should we focus our energies now to get the most bang for our buck? And it was interesting, but the research itself was interesting, but the whole sort of lab setup and everything was left a little bit to be desired. So what I want to say about that is, even if you do some research or you have done some research and it hasn't been the greatest situation, doesn't mean that research isn't for you. It just means that that wasn't the best situation, or maybe it wasn't the right topic, maybe not the right mentor, maybe it wasn't the right fit. And I encourage you to try again if it's something that you think might be in your future. So after that summer of research, I started applying to grad school, and all of my applications were all about wind tunnels and pure aerodynamics. I was going to be an experimental aerodynamicist, and that's what I wrote all my grad school apps on. And then I took my senior level course on aerodynamics and realized I do not like this at all. So we're going to scrap all of that. And so when I got to grad school, it was like interview time. Okay, I need to go find professors who align with what I want to do. And so, yeah, I don't enjoy aerodynamics. And I mean, I still enjoy it a lot more than like, material science or thermo or, some of those other courses, certainly more than, film history maybe. But I found a great fit in grad school. So working with Professor Lacert was, that set me on the path that I'm on today. If it had not been for him, I probably would have gone to industry. And I'm sure, I still would have enjoyed my job. I still love aerospace, and I'm sure I would have found a fulfilling career. But it's him that kind of steered me towards this path and a more lifelong research path that has kept me excited about aerospace engineering. So a couple of things that he instilled in his lab, and I try to carry over to mine. I'll just read the quotes here. So first, good design comes from experience, and experience comes from bad design. So, it's okay to mess up. One of the happiest times in my early stages of building my lab was when one of my students came up to my office and was like, oh, hey, Dr. Kaufman, I'm really, really sorry. I think I broke, this piece of equipment. And I was like, okay. All right, I was a little bit worried because this is a little bit pricey. But we went down to the lab and checked it out. Turns out it was just like a fuse had blown or something like that. It was something super simple. Nothing was wrong. Everything was fine. But it made me really happy because I had a student who was, it wasn't trying to hide it. Wasn't like, oh yeah, I don't know who that was that used that last, right? I mean, he owned it and said, hey, something went wrong. I'm not quite sure what it was. And, what can I do? So that's one thing that I want to convey to you. You heard from Dr. Parati. You're going to hear from, four other labs after me. There are other faculty in our department who do fantastic research. Dr. Vasu is doing combustion work. Dr. Shu does controls. Dr. Gordon does like high temperature mechanics. Dr. Ghosh does some really cool stuff with like scales and sort of bio-inspired structures. So, and there's much more. The point is, whether it's me or one of the other folks tonight or someone else in the department, there's a lot of really great benefits from doing research, especially at the undergrad level. So the second thing that my advisor had really stressed is that getting things done is not always what is most important. There is value in allowing others to learn, even if the task is not accomplished as quickly efficiently or effectively. So don't feel like you're not good enough to do research, right? You're in the engineering program. So, you're going to have some basic skills, but it turns out that the type of skills that we want in our lab, like the things that we want our grad students to be doing, they don't really learn as undergraduate students either. We train them. And so it's the same thing with undergrad research. We want to bring people into our labs so we can train them, and so that they can really start producing and making these great discoveries and helping us advance the science. I guess I'll say one other thing that's a common question, which is, hey, how do I approach faculty? There's going to be 5 of us still here afterwards tonight. That's one great way. But just send us an email with your resume. That's a great start. That's probably going to get you about a 10% response rate, though. So come to office hours. You'll probably see one of us in one of your classes. Sit in the front row, maybe the first 5 rows. But get us to recognize you. That's basically what it comes down to. If I have someone who's in my class and comes to me and says, hey, I want to do research with you, and I'm like, yeah, it's great. I've never seen you. That's kind of rough to get them involved in the research group, right? So it's sort of like show up, just be present, be engaged, and be curious. So those are sort of my general pieces of advice. Let me quickly go over what we do in my lab, which is that we study adaptive structures and structural dynamics. So I got turned on to adaptive structures because I think it presents a lot of really cool opportunities for unique engineering. And so one of the things that we look at in particular are jet engine blades and trying to make them last longer and operate more efficiently. So for a lot of people, we might think, okay, we're doing aerodynamics, and that's actually not at all what we're doing, because remember, I don't really like aerodynamics. So what we're talking about is really the structure of it. And is there a pointer or no? No, okay, all right. So in the 2 circles on the right, actually, you'll start on the bottom left. This is a picture taken by a passenger on United flight, I think it was 328, something like that. It was from Denver to Honolulu, took off, there was a big bang. That's what everyone on the plane saw, circled for a couple hours maybe, and then turned back and landed at Denver again. Everyone was fine, nobody was hurt or anything like that. But then we've got pictures inside from inside the engine. So this is the very front. We got the fan blades that spin around here, and then you have compressor, combustor, and turbine. And so those are the fan blades. You can see one is missing, and the others are kind of chewed up. Of course, that once one goes missing and shoots through the engine, it's going to chew everything up along the way. The basic idea of it is, if you take a paper clip and bend it back and forth, it's going to break. If you bend it back and forth a whole lot each time, it breaks really quickly. If you bend it back and forth just a wee little bit, it lasts a lot longer. And so that's basically what we're talking about. If we can reduce the amount of vibration, then we can make these things last a lot longer. We can increase the maintenance interval. And the fun thing, that's sort of the civil applications. Most of our funding actually comes from military applications, because now you can go after more aggressive flight and performance. Things that you wouldn't even try on a civilian aircraft. We take these really complicated, complex structures. So even just taking one of those, it's hollow, it's got internal geometry, it has twist, camber, taper along its length, the chord changes along its length, all kinds of complicated things. And we say, hey, let's model that as like a really simple flat plate. And it works really well, actually. We retain the key fundamental dynamics. And so we can do lots of research with just these academic sort of fundamental models. We love our cantilever beams. We do work with them. And then we have some other applications where we think about even like some biomedical applications, perhaps of maybe we can mimic muscles or something like that. A student who is looking like Parkinsonian tremor, for example. But again, all on sort of the dynamics structure side of things. I'm going to skip through a couple of these because, again, they're just kind of eye charts. We take these again, the complicated structures, break them down to something simple. We try to develop simplistic models or low order models anyway, something that we can run really quickly. You know, we don't want to spend our time doing a 40-hour finite element simulation when we can do a 3-second MATLAB code or something like that. And so we can get a lot of results much more quickly and you know, still see results that work out well. We always try to run experiments. And so like on this particular example right here, the blue line was our model. And then all those dots along there are, you know, individual points that we had. So what we were trying to do was reduce the vibration of our structure. And so we started off with like a normalized magnitude of 1 over there. And so on this particular one, we only reduced the vibration by like 6%, right? From 1 down to like 0.94. But the key thing was that we were able to see, you know, at what frequency can we reduce it the most? And that was the key thing we were trying to predict, and turns out we could hit that pretty well. Again, even with these really simplistic models. So some other things that we do on the structural dynamics side, we've looked at like droplet dynamics and spacecraft cabling. That's actually a really cool one, I think. Excuse me. So spacecraft cables, things that we don't really think about, but spacecraft can have a significant portion of their dry mass tied up in literally just the power and data cabling that runs between all the components. And like even like 10 or 20%, it's just like the copper cables. It's kind of weird to think about. But how these things are kind of put together is you start off with like your individual wires, you know, like the same wires you would use like with a breadboard, that sort of thing anyway. And you twist 2 together as pairs so that you reduce the interference, and then you bundle a bunch of them together. Then you stitch them together so that they're not kind of flaying out apart, and then you overwrap them with Kapton. All right, am I on the right? All right, so I've got a satellite person here who's like, yes, you're correct. So the interesting thing is, the mass is so great that it actually starts to affect the whole structural dynamics of the entire satellite. And so, so we were trying to develop a model, and what we found is it actually really matters like who does this process, because it's all done by hand. And so like one person would wrap it really tight, and the other person would wrap it, they thought they were wrapping it really tight, but it wasn't quite as tight. And so it turns out that the damping varied by who actually was doing it. So that was kind of an interesting result from that. All right, so we also like backyard engineering in our lab. We've got a continuing project that's been running for like 4 years where we keep testing stuff, and we've been working with a couple of different companies doing similar things where it's basically, hey, we've got this new thing and we want to see how long till it breaks. So we're like, okay, we'll put it on our rig and we'll just shake it back and forth for like 40 hours and see if it lasts. And so I challenged my students to come up with something for as little money as possible, because we've got other things that can do this, but like you don't want to tie up one of your main pieces of equipment for 40 hours at a shot and do this for weeks on end. And so they said, okay, we'll get a giant aluminum base plate and get like it's basically a pool pump motor and like a simple pulley system and, you know, a little track. And for $500 or so, we can do this instead of, you know, spending 20,000 on it or something like that. So something that was definitely backyard engineering, but actually turned into a couple of honors undergraduate theses. So, you know, if anything's interested in something along those lines, you know, that's something that we love to do with undergrad research as well. I'm out of time, so I'm going to skip ahead and just say thanks to all the students and postdocs and collaborators who have partnered with me. And, you know, my contact info was on the first slide, and I'm sure you can get it afterwards. But I hope you will consider undergrad research. It was really, even though it was not the best situation for me at the time, it was really, really rewarding and set me on a career path that I absolutely love. So hopefully you'll check it out and find something successful for you. Thanks.
Good evening, everyone. My name is Divya, and I'm a postdoc at Experimental Fluid Mechanics Lab. Our lab, it basically focus on the bio-inspired like flight, and we draw inspiration from like morphing wing and on-steady aerodynamics that these natural flyers execute.
Thank you for your patience.
Uh, good. So I can also like you. Oh.
Yeah.
Today I'll talk about some of the work that I did in my PhD. It's on rapidly pitching plates in decelerating motion close to the ground. So, okay. Through millions of years of evolution, natural flyers, such as birds, they have perfected their flight performance to a remarkable degree. They can execute varieties of precise aerial maneuver, including banking, braking, takeoff, and landing. This study, it was mainly motivated by the perching maneuvers of birds, where they rapidly pitch up their wings to a very high angle of attack. This maneuver gives natural flyers control, speed, and precision while landing. Interestingly, we found that the birds, they use this rapid pitch of motion to achieve diverse flying objectives. For example, perching birds, they use this motion to decelerate and come to a complete stop. While hunting birds, such as bald eagles, they use the same motion to slow down while catching a fish out of water and swiftly fly away. So motivated by this observation, we try to investigate how ground proximity, it affects the on-seat dynamics of this perching maneuver, and two, how natural flyers achieve diverse flying objectives by simply pitching their wings during deceleration. Now, when you imagine a body that is accelerating or decelerating in one motion, in one direction, and we allow it to execute a rapid pitch of motion, what this rapid pitch of motion does is increase the frontal area of the body, displacing more fluid around it, and essentially increasing the total air mass of the body. So the air mass formulation in one dimension can be represented by the given equation. Here, the first term on the right-hand side, it represents an increase in drag due to frontal area expansion, which in turn leads to an increase in total air mass over time. Now, when the body is trying to decelerate, this increase in total air mass actually makes the body difficult to stop by producing net thrust to the second term of this equation. So what this tells us is that precisely tuning the timing of frontal area expansion during perching maneuver is crucial for optimizing this maneuver. So to understand this, in this study, we created an asynchronous motion between the deceleration and pitch of motion of the wing. So to achieve all these goals, we put a finite wing inside a towing tank, which was filled with water, and we towed it along the length of the tank by using a linear stretch traverse. To execute the rapid pitch of motion, we used a rotary motor, and we used second linear stage to vary the distance between the wing and the ground. Our setup, it was instrumented with the force sensor to measure the forces acting on the plate, and we used 2D planar PIV to compute the 2D flow field around the plate. So in this study, we use a rectangular wing platform with an aspect ratio of 3. Now, to simulate the perching maneuver, we first towed the wing along the length of the tank, and when the wing reached a specific point, as indicated by T star equals to 0 in this plot, we initiated the wing deceleration. Now, this wing deceleration was coupled with the rapid pitch of motion, essentially representing the perching maneuver. To create an asynchronous motion, we extended the deceleration time compared to the pitch of time, and we created two time offset scenarios between the deceleration and pitch of motion. And we represented at T star offset equals to 0 and 0.5. Now, when we analyze the evolution of instantaneous lift at T star offset equals to 0, we can see that the execution of this rapid pitch of motion during deceleration, it causes a rapid increase in the lift coefficient, essentially representing, reaching the peak value after a certain time instant. Now, after this initial peak, the wing experiences a rapid decline in the lift coefficient. Now, when we increase the ground proximity, we can see that this peak lift coefficient, it becomes more pronounced. Now, when we focus on the drag plot, we see the similar pattern as seen in the lift coefficient. The instantaneous drag, it increases with the execution of this maneuver, and the drag coefficient, it decreases later in the maneuver. Now, when you compare the drag coefficient between the two ground heights, we can see that the initial peak drag force, it is not influenced by the ground proximity. However, as the wing approaches the end phase of the maneuver, the wing experiences a rapid decline in the lift coefficient or an increase in the parasitic thrust. So to better understand this, when you analyze the PIV, what we see is that the execution of this simultaneous deceleration and pitch of motion, it causes the shear layer to separate, forming counter-rotating leading edge and trailing edge vortices. The key difference between these two ground proximity is for the near ground case, this vortices, it interacts with the ground, leading to an enhanced lift force. Additionally, we also observed the formation of dipole Z between these two counter-rotating vortices for the near ground case, which is represented by the right plot. We can see that this Z, when it impinges on the ground, it sets the it spreads the state vortices further apart. This can explain the rapid drop in the lift and drag force at the end phase of the maneuver when the wing was very close to the ground. The rapid pitch of motion and the resulting formation of dipole Z. This velocity field animation, it shows that for a T-star obstacles to zero case, this dipole Z is much stronger, as indicated by this larger high intensity contour region. So after this dipole Z, it interacts with the ground. After it interacts with the ground, it reverses and it gets reversed, producing parasitic thrust. Interestingly, this reverse hunting birds like bald eagles, they can harness this parasitic thrust, reverse it as a parasitic thrust to accelerate after catching their prey. So this is the findings that we got from our study. Yeah.
Great, thank you. And that was Divya from the Experimental Fluids Mechanics Lab. Next up, let's welcome to the stage Dr. Duval Pereira to learn about the U-Space Lab. Thank you.
Testing. Hi, good evening, everyone. My name is Paula. I'm new to UCF, so you probably have not seen my face around yet. But next semester, I'll be teaching space systems concepts, so register for that class. It's going to be cool. And today, I'm here to talk a little bit about my lab, the U Space Lab, or UCF's Space Exploration and Spacecraft Engineering Laboratory, which I'm just starting right now. And a little bit of a background, I finished my PhD a couple of years ago. My PhD was on space systems from MIT. And yes, I miss seeing the snow, but it's okay. At least in here we have Disney World. And I did a master's in aerospace engineering, also from MIT, a master's in thermal engineering, 2 bachelors, one in mechanical engineering and one in business and management. And on that note that Dr. Kaufman mentioned that he started doing his undergrad in research in his undergrad, I started doing research on my first year, my freshman year of undergrad. And it was really cool. I never stopped. I ended up traveling to 4 different countries to do internships and do research internships at 4 different countries. And I really enjoyed it. And that's when I finally moved into doing master's and PhD. And just a quick comment, I've done a lot of things related to space. I've designed, built, tested 3 CubeSats. I've operated over 400 passes. I was a NASA JPL visiting researcher for 9 months. I'm the chair of technical affairs for the AIAA Small Satellites Technical Committee. A lot of things regarded to ascend conferences and space exploration, and also co-lead on the Ocean Worlds Working Group. And all of that to say, I really love space. So there is a lot of things that we are still up for learning and up for understanding in space. And a lot of things that we want to understand require new technology development for us to be able to get to the point of understanding those things. And so that's what my lab does, and that's what I want to do. I want to develop technology for exploring space, especially through robotics mission, while doing all things to also enhance life on Earth. And yes, this is a very, very broad, big vision, and that's divided into 3 main topics. I'm working on innovative space exploration concepts or architectures. I'm going to talk a little bit more about that in a moment. I'm also working on next decade's technology, which I'm going to explain in a moment, and in-orbit demonstrations. So to begin with the innovative space exploration architectures. Basically, there are a lot of different ways in which you can explore space. Some of them are very typical, some of them are different, and I'm trying to work with students and work with other people in other different universities to have new ideas and think of different ways in which we can explore space. And that's on the concept level, so it's not something that is going to go to space tomorrow, but it's something that could go to space in a couple of decades, maybe 5 years, if we're very hopeful, and could change the way we do space exploration. So one of the ideas was from a master's student, this thing's falling, was from a master's student back at Florida Tech. And we did his master thesis on developing a swarm of CubeSats for exploring Uranus. And the idea was to try to optimize how much mass we could take to Uranus and how fast we could get there. And he did all the orbital calculations. We got all the delta V that we needed, the kind of rocket that we needed to launch. And then from the mass that we had available, we started to see what kinds of spacecraft we could fit in there. And we ended up with 4 sets of 4 CubeSats of 40 kilograms each of them with which kind of CubeSat with different kind of payload for exploring Uranus. And it was really neat. We were able to close the science mission and also close the engineering mission, and we presented it at 2 different conferences, and we are now working on a paper for a journal. And some other architectures or some different ideas that we are working on right now, I've submitted on 2 different proposals. So FYI, in academia, your life depends on proposals. You submit proposals to different organizations, most of them government organizations like NASA and the Department of Defense. And if they like your proposal, they give you money, and with that money, you do the work. So you really need proposals to succeed. And I've submitted 2 in this topic, one of them for a way for managing items on the surface of the moon. We should hear back in the next couple of months. And one of them for a different way for sending power into craters that are normally shadowed in the lunar surface. So hopefully at least one of them is going to be a yes. And if it's a yes, then I would be meeting the students. And I'm also working with a couple of students on mission concepts for exploring Uranus and for exploring Titan, which is a moon of Saturn. On the second front, and the big contribution with all that is to come up with novel missions that will answer scientific questions in a cost-effective way. And I need to run because I have less than 10 minutes left. For the next decade technology, what I mean by next decade is you are relatively close to this Kennedy Space Center. So you probably, if you like space, looked up about a month ago when Europa Clipper was going on a Falcon Heavy. And Europa Clipper is going to get to Europa in about 5.5 years, and it's going to learn a lot about that moon, which is a moon of Jupiter. And after we get information from it, so in about a decade, we hopefully will have enough money, if the Congress gives money to NASA, to develop missions for going further into Europa and exploring the actual ocean. And the magic about Europa is that it has a global ocean of liquid water, so 273 Kelvin or warmer. And that water has minerals, has energy, liquid, you know, there could be life. But for us to be able to get to the water, we need to get through a very thick ice crust that sits on top of that water. And Europa Clipper is going to measure the thickness of that crust. As of now, we don't know for sure, but we estimate that it's about 25 kilometers thick, which is a lot of ice. So my entire PhD was on a way, developing a way to go through that ice. And we used a chamber that was developed by another company to test different kinds of probes, to develop different kinds of probes, and come up with a model that would say, hey, with this probe geometry and input power, this is how fast we could go through the ice and how long it would take to get to the ocean. And it was really neat. And now I'm continuing to work on that. And at Florida Tech, I have 2 students that I could not bring with me, but they are still in there. I don't think I mentioned I was an assistant professor for 2 years at Florida Tech before coming here, between the PhD and UCF. And the students that I have in there are working on developing probes that have different profiles and different heat distributions so that they can optimize the way that they go through ice. And we are first designing a chamber, and we got funding from NASA to develop that chamber. And we hope to have the hardware for the chamber fully done in about 6 months to a year, and then we can start testing the new probes. And another thing that I've been working on is that there are different groups high up at NASA that work on developing roadmaps and developing plans for what we are going to be doing next. So I've been working with people from JPL, from USGS, which is geo stuff, with other different universities, APL, JPL, they're great organizations if you like space. And we are putting together science and technology to work so that we can come up with a roadmap of science questions that can be answered with the technologies that we have, and also technology development that, if happen, could really open up key scientific questions. And we're working on developing this roadmap so that in the future, NASA can ask for those key technology developments from the scientific community. And I also submitted another proposal for astrobiology, for trying to integrate those technologies that we use on the ocean in here to transfer them to the ocean on Europa. And more things about probes, so that in about a decade or so, we can accelerate the development of those faster probes to get down to the ocean of Europa. And finally, the third bullet point, the in-orbit demonstration. CubeSats are super cool. I've worked on CubeSats many times, and I just loved first starting with the design and then machining it, making it, then going to the clean room, putting it together, then seeing the rocket take it up to space, and then going to the Mission Control Center, send commands up and get the data down, and seeing that entire process is really cool. And I think that one of the highlights was one day that we went to Western Massachusetts, and it was a super dark night with a clear sky, and we were able to see a very, very, very tiny sprinkle thing passing through the sky exactly at the time that our spacecraft was supposed to be passing at that point. So we think we saw our spacecraft with our eyes. Not 100% sure if it was it, but we might have seen it, and seeing the full circle is really fulfilling. But this specific situation here was a different project that I had at Florida Tech a couple of years ago for trying to understand what space weathering does to the surface of regolith on the moon and on other planetary bodies that do not have an atmosphere. And we were able to get funding to develop to develop the concept for an Earth orbiting CubeSat that would demonstrate a payload for, in the future, sending it to the moon. And it was really cool. I worked with just undergraduate students on this project, and these are 4 of the undergraduate students presenting at SciTech last year. And we really, really enjoyed the presentation. Lots of people were there, lots of people asked lots of questions, and we were able to close all the technical budgets. And by budget, we just mean what you have, what you need, what you have, is it larger than what you need? Yes, good. No, bad. That's the definition of budget. And we can do that on data, we can do that on communication, we can do that on power, on mass, etc. And all of those closed in the CubeSat, that mission that they were developing as a concept. And moving forward, I submitted a proposal for AFRL to start a nanosatellite project here at UCF. We should hear back in November, AKA this month. I'm also working on with another university to start a collaboration for the NSF Science and Technology Center for building CubeSats in conjunction, these two different universities. And I'm also becoming part of the UCF CubeSat program, which we're starting hopefully this summer. So we should have a clean room, shaker table, and TVAC and all being set up at UCF soon. And so all that together, the contributions that I plan on having to the industries to develop and demonstrate payloads and thermal control systems for use in space exploration, but demonstrate them on board CubeSats. And okay, yes, I still have 3 minutes. And you might be asking, how can you join? So I started a form and sorry, it ended up becoming quite a long form. So it's good that we have 3 minutes, but it might not be enough for you to fill out everything if you want to do it now. But it's a form with a lot of questions, and it has two different sections. One section is asking about you and who you are. The other section is about your plans. And if you fill it out, and you that will receive a note, and from that note, I'll be able to read more about you. And if I think it's a good fit, I can reach out. Jeff Kaufman mentioned that sending emails with a CV is a good thing, but as he mentioned, the probability of hearing back is like 10%. And yes, I sign on that information. I agree with it. So if you fill out the form, I'm going to know a lot more about you. So the chances for me to reaching out to someone who's a good fit is much higher than if you just send a random email. But it also doesn't mean that you cannot send an email. And if you need to find me, my door is very easy to identify. If you go on the 3rd floor on Engineering 1, there is one door that has a zillion stickers. That's my door. And I have a tiny wheel that says when I'm in the office and when I'm not. So if I'm in the office and you see a bunch of stickers, you can knock and we can chat too. Okay. Still have a minute and a half. Cool. Okay. Thank you.
All right. All right, next up we have Adam Collar. He is a graduate student and he's representing the Propulsion and Energy Research Lab. Awesome, thank you.
Okay, cool, I'm coming through. Okay, well, it's a pleasure to be here. Thank you all for having me. My name is Adam Kotler. I am representing here tonight Dr. Kareem Ahmed, presenting and talking about what we do at his lab, the Propulsion Energy Research Lab, specifically the hypersonics division, right? So a little bit about me. I recently graduated with my master's degree from Dr. Ahmed's lab, with Dr. Ahmed's lab in mechanical engineering last fall in 2023. And as for my undergrad, I was actually right across the river from Dr. Pereira at Boston University. And so while I was there, I was actually a machinist for 4 years, and I took several internships in the launch and space industry. I had a couple stints in California. And when I was in California, I worked at Stellar Exploration, and what we did was design the propulsion and the space vehicle that delivered and executed on the Capstone mission, which flew aboard a Rocket Lab vehicle back in 2021, summer 2021, and the mission was to image the far side of the moon. Now, I'll talk a little bit more about my stint in California later down the line, but I want to call back something that was presented in Dr. Kaufman's presentation, which is that it was a quote by Theodore von Karman, which said, "Good design comes from experience, and experience comes from bad design." And so a couple weeks ago, Starship, SpaceX did something pretty damn ridiculous, which was catch the Starship vehicle as it descended, performed its descent maneuver, and then landed back on Earth. And I think the Theodore von Karman quote really exemplifies, or really, I guess, Starship's maneuver and the feat that they accomplished really exemplifies that quote. About a couple decades ago, Elon Musk took the risk, and no matter what you think about him, he was the first person to take the risk and try and do all of that on his own, and say, we don't need government to do this. I'm going to spend all of my own money and take the risk to do heavy launch in my own company. And so they had several failures leading up to that point. And it was only by taking this risk at such a grand vision that they were able to really accomplish something and really guarantee for the United States and the United States military air superiority across the geopolitical landscape. Right. So this is going to be very important later for some other stuff I'm going to talk about. But now I'll proceed into the research. And what I'm presenting today is modes of detonation for 21st century hypersonic flight experiments. Right. Okay. Okay, so what do we do at Dr. Karim Ahmed's lab? Well, at our roots, we are a high-speed combustion lab, and so we study we investigate the fundamentals of combustion as they pertain to hypersonic flows, right? And so, pretty much anything under the sun that you can think of pertaining to combustion physics, we study it with hypersonic flow free streams passing across it. And with this, there are novel forms of combustion. Conventionally, you have deflagrations, but we also mainly study detonations as well. So, okay. So what are we looking at here? So on the left, we have what is called a stabilized oblique detonation wave. This image here was taken by my mentor, Daniel Rosado, was published in the Proceedings of the National Academy of Sciences back in 2021. And this is a unique mode of combustion stabilized in a hypersonic flow, and it stabilizes between the micrometer to meter length, or sub-meter length scale, which is much shorter than the average flames or the typical flames that you'd find in typical combustion devices, stabilizing at longer length scales. And what you have on the right-hand side is what we call a normal detonation wave, which is a detonation that stabilizes at a slower Mach number than one might see for an oblique detonation wave, right? Okay, so I'm going to sort of trace through the state-of-the-art or the literature that has led up to this state-of-the-art and enabled us to really contribute to this field for detonations, and then from there you'll really talk about why I'm here. So, all right, so what is a detonation? Everyone thinks of detonations. You think, oh, it's just a bomb, right? But really, it's got more fundamental roots than that, right? So what I've got here is a figure of pressure versus volume. So you get pressure on your y-axis and your volume on the x-axis. And so I've identified 3 points here. Really pay attention to the red and the yellow ones, and we'll start with the yellow one. So that's a deflagration. What is a deflagration? Well, it's any other flame that you might see on a regular basis. It's slow. The reaction physics occur at very slow rates, and you typically stabilize them over longer length scales. And so concomitant to the stabilization of this flame is some amount of heat release, right? And in a thermodynamic system, when you react some chemical composition, what occurs concomitant to that chemical reaction is this release of heat, right? And so there's some finite measurable heat associated with that chemical reaction. And so that for the most part defines a typical deflagration flame. Now what happens on the opposite end of the curve? Well, we get what's called a detonation, right? So this is a process which occurs for the most part at some constant volume, and as this reaction proceeds, you get a significant hike in your pressure. And the significance of this is that you can really release a lot more energy, a lot more heat into your system per unit mass compared to a deflagration. Okay, so why do we study detonations? Specifically for hypersonic propulsion. Well, this ability for the detonation to release a lot more energy per unit mass, you can really liken that to the miles per gallon that you're running on for your engine, right? Whether it's a rocket engine or whether it's a air-breathing propulsion system, right? And so in aerospace and hypersonics, mass really means money. If you can reduce the amount of mass that you have on board, whether it's in your dry mass or your wet mass, such as the fuel that you carry on board, that means you have room for other things, right? You can add room for payload, and of course, if you can add more payload per unit mass, then you've reduced the cost per launch or the cost per flight, right? So that's very valuable. Maybe it's not mass that you want to save on. Maybe you want to perhaps keep the same mass, but then for like a defense application, you improve upon a different metric. Usually it's called lethality, right? And so, right, if you can increase that kinetic energy of your system, then you improve your ability to maximize damage at your target location, right? So, long story short, for dual use aerospace applications, a detonation can prove to be a very useful and advantageous mode of combustion, which we can leverage for future hypersonic propulsion systems, right? Okay. What are we looking at on the far right over there? Well, that's a conventional scramjet engine. And what's really important to highlight there is really what I just said. It really just visualizes what I just said earlier. You have a longer length scale flame, and for the most part, right, that characterizes the state of the art and what we can do in hypersonic propulsion today. And what happens when you use this mode of combustion is that you have to have stabilizing flame holders, which increase mass and overall increase the length scale of the vehicle and propulsion system that you carry on board. So if we can use a detonation, which, as I mentioned before, capitalizes on that small length scale structure, you can very significantly reduce the length of your high-speed flow path in your engine, thereby reducing system complexity and saving a mass premium for your payloads or whatever your mission specifications are. Right? Okay. All right, so I'm going to try and go through this as quickly as possible, but really I'm tracing through the state of the art that brought detonation research to where it is today, especially in the context of high-speed flow. So starting on the left, this work here, detonation structures behind oblique shocks. This is a paper. That man, by the way, is at the Air Force Office of Scientific Research and is currently funding my PhD. But basically, what is the structure of an oblique detonation wave? Well, if you've taken high-speed physics, you know that if you have a high-speed flow that hits some disturbant boundary, you create some shock. And across that shock, you have some concomitant pressure and temperature, some state property rise. This accelerates the chemical reaction kinetics. And at some point, if the energy of your free speed is your free stream is fast enough, you will culminate all of your chemistry at some reaction zone called a ignition delay length. And what happens at this ignition delay length is you've sufficiently succeeded the chain branching and chain limiting reactions which govern your which prevent your chemistry from reacting. So if you can auto-ignite, if you can reach this chemical ignition delay limit, then you can stabilize some flame or start some reaction fast enough to sustain itself, right? And so you simply have some induction zone behind your non-reactive shock. You release that heat, and these deflagration waves coalesce on top of each other, forming this reactive shock known as the oblique detonation wave. And on the right, we just really have the conservation relations, which explain the stabilization criteria necessary to have a detonation. Really, just the important details of it all. And so a lot of experiments through the past several decades, leading up to the early 2000s, sought to observe this phenomenon in some experimental configuration. Now, the problem is you need so much energy to stabilize an oblique detonation. And the only way to do that for these folks to do that was to literally shoot projectiles in some gun barrel launch system with a composition of reactive mixtures. And what we just have here are a series of these projectile experiments which were able, using Schlieren imaging, they were able to observe the different modes, the different regimes and gas compositions at which you were able to stabilize an oblique detonation, right? And of course, these are at very small scales, right, at the size of like a 9mm bullet. And the time scale of experiments were very short. They're on like millisecond time scale. And so these time scales are not really relevant and not really exemplary of what you might find in a propulsion system, right? Propulsion systems you have to operate for hours, sometimes days at a time. Okay. And so this just highlights a novel set of experiments performed by some colleagues in Canada. Really, we highlight this set of research because they were the first to really observe several different modes of oblique detonation waves, catalog them across their different regimes, and then provide some mapping, some means by which to map the regimes and the state properties and the geometric boundary conditions at which you may be able to satisfactorily stabilize an oblique detonation wave. Okay. All right, so the problem with all of that is it's as I said, they occur at very short time scales, right? The experiment durations at very short time scales, and the length scales at which they experiment are very small, right on the order of like the size of a bullet. And so we took a different approach at Dr. Karim Ahmed's lab, and instead what we did, in order to achieve that high Mach hypersonic free stream necessary to stabilize that oblique detonation wave, we literally take a rocket engine, blast it through, blast those high temperature gases through a converging diverging de Laval nozzle, acquire that free stream, and then from there we simulate a stabilizing wedge inside the flow, and then from there inject our fuel and stabilize an oblique detonation wave on the order of minutes. Okay, so how do we do this? Well, you know, this just sort of goes through the typical box problem one might set up when doing research, right? I have a set of boundary conditions which would stabilize my oblique detonation wave, and all I'm doing is just identifying the math and the relevant conservation relations which allow me to stabilize that flow, right? So we start with compressible thermodynamic flow relations. We have a chemistry model. This allows us to figure out the conditions at which we will be able to auto-ignite our mixture and stabilize that detonation. We from there design the ramp necessary, right? The ramp geometry necessary to stabilize that oblique detonation wave within the time scale, and then from there identify whether or not we're within the limits of the conservation relations for stabilized oblique detonations. Okay, and this is a schematic of the rocket engine that we use, right? This is a typical hydrogen air-breathing rocket engine. We deliver our fuel, hydrogen fuel, and our air into our chamber. We realize pressures and temperatures on the order of 1,000 degree Kelvin. Pressure is about 5.7 megapascal in our mixing chamber. We light with a spark plug, right? We generate these very high pressure, high temperature gases. We expand through our CD nozzle, achieving velocities of Mach 4 to Mach 6. And then we have our test section all the way at the end where we stabilize our oblique detonation, right? So this is the facility that we use. And so really, right, and so we're able to take this Schlieren imaging, right, those monochrome figures that you see in the test section, and then from there compare the length scales of our calculations to what we've observed in the experiment, thereby confirming we have a detonation, right? And that's really just what this fancy figure goes to show, right? This all formed the basis of my master's thesis, and really, I'm just trying to give you guys a flavor of what you sort of do at the lab when you really get into the weeds and the details of the work. This becomes our day-to-day. We perform these combustion experiments, right? And so I mentioned earlier that you have two different modes. You have an oblique detonation, right? This mode is mode 3, categorized at the top, and then mode 2, you have your normal detonation, which is characterized by lower stagnation pressures and, for the most part, just a little bit cooler temperatures, right? Okay, some more boring stuff. So, well, why is this relevant? Why is this novel? Well, back in the day, back in around the 60s, some guys, really the start of all this research, this guy, Nichols, he thought he had stabilized a normal standing detonation in his facility using an under-expanded jet. I went through a lot of work. If you find me after I tell you all about it, but I went through a lot of work and did all sort of the reverse engineering, the reverse science of their work, and was able to identify that really they didn't have a standing detonation. They just had a form of shock-induced combustion, and that really when my mentor and I, when we did the experiments in the test section using that stabilized hypersonic flow, we were able to really capture for the first time a very closely coupled normal shock and a high-speed combustion detonation for the first time. Okay, so why do I call all of this boring? Well, when I was really in the weeds and the details of doing this analysis, I was very excited about it, very happy to engage in this work. But our Air Force stakeholders came back and asked us, well, they raised the point. If you're testing it on ground, are you actually testing the real phenomenon? So it was a very interesting question, right? And I'm going to reframe this question a little differently. Take Usain Bolt, really known as the world's best 100-meter dash, but only when he is fed the proper diet and he has been going through the right training. Now, how does that analogy have anything to do with everything we're doing? Well, the detonation has to be fed the right quantities, the right composition of fuel and air mixture in order to detonate. And if we're doing it on ground by reacting all of our fuel and releasing all that heat, we're kind of cheating the system a little. We're not actually using the so-called virgin free stream air that we would have in a real flight system. And so the Air Force came to us and they raised a challenge. Can you fly this thing? And we decided we'd take a pass at it. And so it was this type of vision, this type of work that really drew me to UCF, right? So you see, when I was in California, my friends and I, we had moved out there during the heat of COVID because we figured when the work at Boston University went to sort of virtual learning mode, we decided that we'd sort of take advantage of that, move out to California, get a jump start in our careers. A few months later, my friends told me the true nature of them moving. It was to form a startup. Now, I was bewildered. I was absolutely bewildered at this because they had worked so hard. We all worked so hard to guarantee for ourselves stable careers in the aerospace and the launch industries. However, I saw them throwing all of that away, right? They threw away guaranteed, safe, high-paying jobs to execute on their own vision. And it is when I saw this experiment being performed at UCF that I decided, I'm going to pursue my own vision. I'm going to do the exact same thing my friends did in order to become a better version of myself. I won't see that just by going straight into industry. There's a limit to what I could achieve, and there's a limit to the type of person that I could become. And so we decided instead to form a flight experiment. And this is really why I'm here today, to show you all the vision that we're executing at Dr. Ahmed's lab, which is to fly an experiment capable of stabilizing an oblique detonation wave. Okay, so how are we doing this? Well, it's a multidisciplinary RDT&E effort in which we're investigating ODW fundamentals, flight engineering design, material limits, numerical simulation, and heat transfer. We have a bunch of other stakeholders, including Stanford, University of Illinois, and of course our Air Force stakeholders, among others. On the right-hand side, we have Kratos. They provide the vehicle for us. We need a very high-speed boundary condition in order to stabilize the oblique detonation wave, and so the apparatus by which we achieve this high-speed boundary condition are sounding rockets, which get us up to Mach 10. All right, so we come together, we provide the payload, they provide the vehicle, Mach TB, government program, they serve as the mission integrator, and we all culminate together, and over the period of just over a year, we collaborate, and the flight culminates at the NASA Wallops Flight Facility, where we will be launching Q1 2026. And so this is sort of what the system has come to, right? So two Terrier Mark 70s as the first and second stage. So on the third stage, we have an Oriole Chem 22. And our payload forms the very front end of this stack up. And so what we have here is an analog to what we have at at Dr. Ahmed's Hypersonic Propulsion Lab. We have some high Mach 10 free stream flow that goes through a trench, and we have our detonation stabilizing device at the end. Combustion gases exit at the end, right? So this composes, right, this is sort of a flavor of the outer mold line that we've developed for our payload. On this project is actually, it's a little bit of a unique role that one might assume as a PhD student. I serve as the chief research engineer. And so what that means is it is my duty to engage in the pedagogy, engage in your learning as undergraduates and graduate students, and not lift a finger. If I'm doing my job correctly, then all of my students are doing the learning for me, and I'm not lifting a finger. And that's what I want to show you for the rest of this presentation. So we have 4 teams: structures, plumbing and electronics, integration, and technology maturation. And so this is the structures team. This is my student Spencer Smith. He's 2 years younger than me. And what we have are a collection of undergraduate students, mostly taken from the Knight's Experimental Rocketry Group. And they have been doing all of the design for the outer mold line and the aero shell for our vehicle payload. And here's some of the work that they've done. Really, if we take an exploded view, we get to look at the inside and see all of the work that they've been able to accomplish over the past year. It's been a significant effort, but with our stakeholders, with the guidance of our stakeholders, the graduate and undergraduate students on the structures team have been able to develop a fabricable, approved design that we are now pushing through manufacturers. So what we're doing is we're printing our Inconel aero shell. We're isogriding it to maximize the stiffening. And we have sort of a multi-layered thermal protection system composed of carbon phenolic on the outside, as well as some other materials, which is not shown here. All of that gets bonded together. And on the inside, we have our electronics and plumbing secondary structures, right? And so we're really composed of two sections. We have the forward end, the forward module, the clamshell. This houses our experimental section. And on the back end, we have our wrapped payload support module. This holds all the guts, the electronics, the plumbing bars of our subsystems, right? It's hot. It's hot. When you're flying at Mach 9, Mach 10, you get really hot, right? And so we need novel ways to cool. I'll spare you all the details here, but right now the team is investigating multiple ways to cool the system. And really the only way to do it is to use a combination of ablatives, regenerative, and transpiration cooling. And so these are some of the novel scientific investigations that a lot of the graduate and undergraduate students on the structures team get to perform. All right, so moving on to plumbing and electronics. So this is a bit of a unique system. This is a subsystem that is led entirely by undergraduate students. Every single one on this, every single student on this subsystem is an undergraduate. This group is led by Andrew Shack, an undergraduate of mine. Funny story, I was testing a different engine night. It was like 12 a.m. This guy saw me. He was like, wow, that is so cool. Can I help out? And I was like, yeah, sure. Really, really, I was just waiting for him to like leave a lot of the other undergraduates, but really he stuck through it, and he ended up testing with me for the next 7 hours up until 7 a.m. It was his first time, and he just took orders, and he really had this fire within him that enabled him to really lead the ball on testing for me. And so he stepped up to the bat, and soon after, the rest of the team formed, and all the other stepped up as well. And so here's what they've been able to do, right? So we have this payload, we have the structural subsystem carried by a different team, and these guys, also poached from the Knight's Experimental Rocketry Group, are able to assemble all these electronics and plumbing systems for us. They come up with these neat, fancy diagrams, but of course, we get to purchase it all and get to test it, right? This system has come up to be about $200,000 just in instrumentation and flight computers, just to enable us to collect data in our experiment in flight. Of course, we have a plumbing system. Our experiment is a combustion experiment. It's a combustion device, and so we need fuel to react with the air, the high-speed free stream air. And so what the plumbing system subsystem team has designed is this plumbing system, which is powered by high-pressure nitrogen gas that delivers the fuel through the plumbing system and eventually through the external aeroshell. And of course, we have ground test and data acquisition systems. Before we go and move into flight, we have to de-risk all the technologies that we're going to put on our flight payload. And so we do all of our testing in the canopy and in the new hyperspace building, Dr. Karima Med's lab. And really, this visual is just giving you really just showing the level of detail to which we design and really tailor our ground electronics. And so what we're looking at here is a power distribution board. This is a flight PCB designed by Vera Fedor, and she was able to really put all this together over the span of a few months. And really, this is going to be the sort of the heart that really controls and directs all of the signals and the the power that drives our electronic systems and our instrumentation. And so all this level of detailed work performed by undergrads like yourselves to accomplish our grand mission of hypersonic flight. So thank you very much, and be happy to answer your questions at the session soon.
All right, and last but not least, from the Astrodynamics Space and Robotics Lab, we have Dr. El Gahari.
Oh, okay. All right. Good evening, everyone, and thanks for sticking around that late. It's close to my bedtime, so hopefully I'm not gonna keep you up very long. I guess I'm your co-advisor, guys, right? Like I'm advisor for this. Okay, okay, cool. So one thing for the future is we need to have pizza in these events.
We do
Okay.
yeah.
Yeah, so that will get people more excited. Definitely pizza, especially that late. Okay, so very quickly, I'm gonna speak a little bit about my lab. It's the Astrodynamics Space and Robotics Lab. We do we have a few projects that they can sometimes seem a little bit not connected, a little bit all over the place, but they kind of get, we don't have a pointer, right? Okay. So the orange star is where everything kind of get together, the fundamental research that we do, nonlinear dynamics, computational sciences, and control theory. In astrodynamics, we're interested in space-based space surveillance, so constellations of satellites, monitoring and observing the space domain. Another part of that is the accurate propagation of uncertainty. For the space component, we're looking at, in collaboration with the physics department, the dynamics of lunar dust, so how electrostatics affect the motion, levitation, and how to mitigate the bad effects of lunar dust. And finally, we're looking at real-time guidance control in entry, descent, and landing. We also have a robotics platform where we conduct some experiments, and that's where most of the undergraduate students in my lab can participate. Okay, so very quickly, there is an increasing interest in the cislunar domain. Cislunar is the area between Earth and the Moon, beyond the geostationary orbit, all the way to the lunar orbit. A lot of interest there, a lot of missions, as you have heard, that will be landing and have landed on the Moon. Also, the Gateway, NASA Gateway, which will be launching as well hopefully, very soon. And one of the things of interest for the DoD, the Space Force, Air Force, is how can we monitor that new space domain? How can we basically effectively cover that area, detect anomalies, detect traffic, or manage traffic in that area? So one of the things we're working on is basically how to answer that question. And answering that question has a couple of ideas: how to design constellations in cislunar domain. Now, anyone here did orbital mechanics? Okay, with me? You're lucky. Okay. All right, so some people will do it next semester. I'll be teaching it, and we do some three-body problem in there. Essentially, the main distinction between the three-body problem and your typical Earth orbiting satellite, the two-body problem, is that the number of trajectories increase significantly. You have an infinite number of possibilities. Trajectories can be chaotic. There are trajectories that can take you from Earth to the Moon without applying thrust. So it can be very, very tough to monitor that domain. Additionally, it's extremely large. Okay, so it's about 40,000 times bigger. Anyway. All right, so we're, yeah. So basically the idea is very simple. If you have several satellites looking at several targets, you can essentially, via an idea very similar to triangulation, estimate both the satellite location and the observer's location, the targets and the observer. And this is what you're looking at here from a trick using a very fundamental idea that two overlapping planes produce a line, and two overlapping lines or intersecting lines gives you a point. So that's the fundamental idea right here. It's not, it's not rocket science, okay? So basically, what you have is you construct, you have cameras looking at targets, and basically several cameras looking at several targets, and from that mess, you can start estimating where the targets are as well as where the observers are. Because, as I said earlier, the domain is quite large. We will not have very good custody on satellites going in that or moving in that domain. So we might as well be able to estimate where the observers are as well as the stuff that we don't know about. So back to Dr. Pereira's example, when they were looking at the CubeSat in Boston, right? And they think that this is it, that's something that would help, okay? So, and we will look at uncertainty quantification as well. So we did some experiments here. These are a couple of typical cislunar orbits. There is a DRO orbit, NRHO 92, that's where the gateway will be. That's a near rectilinear halo orbit, 92. And basically, we're trying to look at targets. We have an observer on the lunar surface, an observer in DRO, and we're trying to estimate something that is along the gateway orbit using that idea of several things looking at that orbit. So there's a lot of stuff here, but essentially we're doing kinematics. So just by looking at the target, doing something called initial orbit determination. So we're not including any of the dynamics of the cislunar or the cislunar dynamics in our estimation. Okay, so this is sort of your first step in identifying an orbit. And then you basically call your filter, your Kalman filter or whatever filter you feel good about. So the results means that this worked, basically, and worked pretty well. These cases were previously divergent in the literature, and we were able to show that we could do that. That's one other orbit. I don't know why the images look like that, but that's another orbit that I just mentioned. That's a 2-1 resonant orbit. Essentially, that orbit gets you from Earth to the moon without applying thrust. Okay, and that freaks out a lot of the people in the DoD because that's a free transfer. Okay, you can put an orbit in GEO. It starts at GEO, which is the geostationary orbit around Earth, and you can end up on the lunar surface without applying any thrust, without doing anything. It's a free transfer. Okay, and that's crazy. That's crazy stuff right there. It takes about 14 days to do that. Okay, and that causes a lot of anxiety if you want to monitor that space, because things can go in and out of that space without doing any thrust or any maneuvers, and you will not know about it. Okay, they will just pop up. Okay, so we applied the same concept of putting observers on various locations along that orbit. So we have a few in L4, L5, and at GEO and around the moon. And here we apply the Kalman filter, essentially to basically capture that target moving between the various phases of that orbit. Now, the idea here is you don't have continuous coverage. So you're in and out of coverage. And that's a big problem because, again, that space is quite large. It goes from the Earth all the way to the moon. So you cannot have satellites covering all of that path. It's infeasible. So by putting a few satellites here and there, you can essentially keep track of a target and lose custody of it and capturing it again, and lose custody and again capturing it again. This is not optimized, but that's a few satellites per orbit or per region. And that shows you like what is in the red and the black. Those are the boundaries of your estimate, and you see they're diverging and then coming back again and then diverging and then coming back again, which means in these regions, you lose track of there are no observations. So that's cool. Here we tested many targets and many observers up to 5 and 4, and these errors are in meters, absolute errors, and obviously pretty good. The other area, how much time do I have? Only 5 minutes. Okay, cool. So we do cool stuff at Astrodynamics. Please join us. Anyway, so that's for coverage simulation. So the first one is, okay, now we have many targets, many observers, and everything looks great. But where do we place these things, right? So you have different sensors, different sensor profiles, different volumes of the space that you want to cover. So that's what we're doing here. We're trying to quantify what is actually coverage in the cislunar domain as a function of the orbits, as a function of the sensor profiles, and a function of what are the target regions. Also, we're looking at tasking, how to use coverage for tasking, and so on. There is no conventional way to define bands of coverage in cislunar domains. So in Earth, you define these dual altitude bands, and you essentially start overlapping geometries and do polygon clippings. So you get these nice planar, shapes. And those intersections define how many satellites are looking at a certain region. In the cislunar domain, because the orbits are quite different, they're not that well behaved, you don't have that description. You don't have that nice form. So we're using octrees, some structure like binary operations to quantify coverage for that, and it shows pretty good results. One thing that we're very happy about is that. So it's an adaptive method that gives you an upper and lower bound on the coverage. So even though this is sort of level 3, which is, let's call it quick and dirty, level 6 is very high fidelity. And you can get a solution very, very quickly in faster than real time, and this is important for tasking, with a lower fidelity type solution. You get an upper bound and lower bound. And think of the tasking problem. If I have an upper bound and lower bound, I can start tasking my sensors to look in these regions very, very quickly, versus waiting for the high fidelity that may be more computationally expensive. So that's one result that we're happy about. The third part in this is propagation of uncertainty. And again, in the cislunar dynamics, now we made a lot of assumptions here just to make it work, because we're not dealing yet with chaos. These dynamics can produce chaos. But the idea here is we can essentially predict where some of those targets, some of those satellites would be in the future without measurements. So we're trying to cover acquiring measurements via multiple satellites or multiple observers, optimizing the coverage of those multiple observers, and in between, we're trying to figure out, when we don't have measurements, how we propagate the uncertainties so we can retask everything to look where we think the satellites are. Okay? So that basically shows that we produce good results. We're looking also into some machine learning stuff for predictions, creating a digital twin that's related to that. That's an Air Force project that we're currently working on. Okay, so on the control aspect, we're interested in optimal guidance, optimal control, applying that in real time. We're interested in some fundamental problems. This is like you do this in elementary school, the cartoon a pendulum. So that kind of problem. So it's very simple. And we're also interested in using machine learning for entry for these types of problems. So that's entry, descent, and landing, or using transfer learning to come up with a guidance law, guidance profile for Mars missions. Okay, so we're using LSTMs, and we train on the Earth model and transfer the knowledge to via fewer data points to Mars, and essentially start testing the machine learning algorithm using LSTMs on Earth, and then on Mars. Okay, so that's sort of the altitude versus time, distance to the target region. So we're trying to do precision landing using that stuff. So finally, oh man, I'm doing well. Finally, we have a robotics platform. We do have a few robots. One of the main things we're developing is that thing. We call it ROAM. And this is one of my graduate students. He was very good at acronyms. I'm not that good. So he created that. We called it Rapid Orbit Motion Emulator. And I get several emails about this. Basically, we have a ground vehicle with a robotic arm, and we're trying to emulate something that looks like an orbit. So in the lab, we in-house developed all of this stuff. We're going to use this for some in-orbit servicing, assembly, and manufacturing type missions, like docking, like getting the two of these to dance together and do some cool stuff. This is our Mach 2. Our Mach 1 looks horrible, but we built it out of plastic. It was a mess, but it still works. But that version 2 is really cool, and we're also building a third version, a little bit bigger, more better electronics, and so on. Okay, so yeah, this is Mach 1. I said it looked horrible. I'm gonna skip the videos. They work. The last thing is the space stuff, and I'm gonna maybe go a couple of minutes over if it's okay. Okay, so lunar dust, that's sort of when I wear my multi-body dynamics hat. Again, it's a dynamical system, multi-body dynamics. You see the equations, they look familiar, a potential and some interaction. The interactive forces are basically electrostatic forces. A lot of stuff is still, we don't understand a lot about how lunar dust interact with electrostatics. The dust itself is very complex in terms of its structure, in terms of how the charges, the distribution of charge on the dust. So we have a project that we're trying to understand how that works, how the dust moves due to electrostatics, due to charge and charge transfer, called tribocharging. I guess we all did the pen in the hair and picked up like a piece of paper. Did you guys do that? You were not curious enough to do that? Yeah, it's a stupid thing, but we all did it. So, that's tribocharging, right? You create a charge by friction. That's basically it. Lunar dust does go through that a lot, and it does have a very significant effect. And I'll show you what. These are some experiments we did in lights, like a multi-body dynamics particle simulations. We're trying to understand how tribocharging operates. Let's see. This, I think, is a longer one. But in any way, one thing that I want to that came out of the initial study is how sensitive, that's the distribution as a function of the charge, okay? And you can see that this stuff started with a 1 millimeter by 1 millimeter by 1 millimeter cube. So we had a concentration of dust that is 1 by 1 by 1 millimeter, and that's in meters. The distribution can go up to meters, okay? So the position, that's the distribution and the standard deviation. You could see that a 1 millimeter, that's nothing. Like that's maybe a few thousand particles. And they can go all the way to about 0.5 meters. Okay, so that's in position. In velocities also, they can acquire quite significant values. So that's one important thing. We're trying to understand this a little bit more, and essentially try to do these sensitivity analysis of how can we predict where dust will be due to the charge, due to the initial charge, and due to tribocharging. Yeah, that's a version of us a year or so ago from my house. So thank you all, and I'll be happy to answer questions.
All right, let's give one more round of applause for all our researchers. All right, and I'd like to invite them all back up for a brief Q&A. here, I'll just give the mic to you, and then if anyone has questions.
This is more of a general. This is more of a general question for like all of you. As a freshman, what should I be doing to get myself ready for research?
Just do it, man.
Before I don't even do that. No experience even beforehand.
Yeah, no, just go into it. I didn't get the time to. A couple of people in that picture, I had two students who started in my lab as freshmen. So I was a freshman, they were a freshman. Like I just started here at UCF, and they started with me. And both of them are doing their PhD with me right now. So one has the MSTGRO fellowship from NASA doing his PhD, and the other is working with on a Lockheed Martin project. He spends every summer in Lockheed in California. So I guess that's some others did start with me as freshmen and didn't continue, but there is no time limit. The problem is when you're a freshman, you haven't taken a lot of the classes. But if you're willing to sort of, push yourself a little bit and start reading about concepts that can be foreign to you as a freshman, you will be just fine. So yeah, if you're interested, just go for it, and you never know. And the sooner you start, the better, because you might not like it. So if you started late and you didn't like it, then there's not enough time to do another one. So if you start early and you don't like it, then you can try another lab and another lab until you converge.
All right, thank you.
Yeah.
A couple of additions in there. One thing, when you start as a freshman, probably in the beginning you're going to be doing the boring tasks that the graduate students don't want to do. Understand that that's not like beneath you in any way, because you have not taken classes yet that have the actual engineering course. So you might be there reading papers and putting on screws on a robot, but that's the beginning. That's how you start, and you're going to grow from there. And one other thing that I'd like to add, that I don't know if it's just like me being picky, but one thing that differentiates the student, at least when I'm talking with them, is when the student realizes that it's not all about them. For example, when you go to a class, it is all about you. You're there because you want to learn, and the professor is there to give you the content and help you create that content. But if you are an undergrad and you are in a research lab, it's not just for you to learn how to do research. That's not how research works. The key is to come up with the new content, come up with the development, come up with results for the research. So if you go with that mindset of you learning is just one portion of it, the key aspect is making the research happen, then it already differentiates the way you see it, and the learning is more like a consequence in a weird way than just like gazing your own belly button.
Yeah, I'd say, I want to echo everything Dr. El-Gahari said. I think he really captured the essence of it. You just kind of got to throw yourself into it. I advise, even as freshmen, as early as you can as undergrads, push yourself to failure, your absolute limits, as early as possible. Develop that grit early on, and if you could do that, then you'll really be able to you'll really be preparing yourself for any challenge that awaits in the future, agnostic to context, whether it's academic or industry. If you can really understand your own limits. And I think you guys are in very unique positions as undergrads where it sort of is the time to do all of that now. And so push yourself to your limits, identify where they are, figure out what you're willing to sacrifice, figure out what's really requisite to your own life, what's enriching, what you can't give up. And if you're not as an undergrad figuring out what those limits are, then ask yourself why you're in college in the first place.
What have you seen the most successful student researchers have in common from before they joined the lab?
For me, I always go back to one thing, and it's the commitment of the student. If a student is committed to do the research, then, it's always like, it's It's hard, it's difficult, there is a very steep learning curve at the beginning. I think the commitment to see it through, right? To be patient, to see it through, to dedicate enough time. One of the mistakes, I would say, to look at the other side, one of the mistakes I see when things don't work out is, I mean, I think it's always a good experience, but sometimes, it could have been better and you see it. And the problem is that sometimes undergraduate students in general, and we the same, we do too many things, right? And then you don't spend enough time doing that research. Research is hard, it's difficult, it's fascinating, but it's difficult, it's not easy. So you need to set aside enough time. If you're taking 5 classes, participating in 3 clubs, doing 3 research experience, it's hard to be successful, right? You may be exceptional, it may work. That's my experience. Is like pick one, and then you can change and set aside enough time so that you can really dive into it, understand if you like it. If you spend a couple of hours a week, it's a waste of time, right? You don't have enough time, you don't spend enough time, you don't learn if you like it or not. So I would say for me, it's always been like the commitment of the student, setting it, and the commitment, like in practical terms, like, yeah, I'm going to see this through, and I'm going to look into the literature, I'm going to learn whatever I need to learn, and then setting aside enough time to do it. That is the main things that I see in successful students in my lab. And I did the undergraduate, been here for 5 years, 6 years almost. As been seeing, like I did research with more than 30 students, and that's always undergraduate students, and that's always been the constant throughout.
Hello. So I'm about to complete a minor in computer science, and I was wondering how helpful that would be in a research setting. A lot. um, current. I'm doing lots of personal projects. I'm majoring in aerospace engineering, but I was just wondering what kind of personal projects that I could possibly work on to help me get into a research project.
Yeah, so I mean, you're in aerospace engineering and you have the CS minor, and is the goal to have some sort of project which is heavily utilizing CS principles? Well, you're in luck because in every subfield of aerospace you could find something, and so I would encourage you to identify a subfield that you really want to focus in on and hone in, and just go for it. Like you could execute on whatever CS principles you want, integrate that with the field of aerospace, and you'll find something. You'll find some diamond in the rough that you can really use to exemplify your skills and your ability to take a problem, build a box around it, identify all the inputs to this box and everything that comes out of that box, right? It's the black box concept. For context, I have a lot of undergraduates who work for me, and like I'd say 5 of them have a CS minor. There's no shortage of chemistry, fluid physics, propulsion calculations that they can automate and efficiently process a lot of data from. And so I think you're in luck. I think you're in a good spot there.
Thank you very much. I appreciate that answer.
Yeah.
To add, I mentioned in the beginning of the talk that if you're a professor, proposals are everything for you. And there is a lot of solicitations so giving a step back, a solicitation is basically what NASA or the DoD or government agency says, this is the problem. I want someone to help me solve this problem. And then they put the problem out there, and then faculty and people from industry and research labs, they propose a solution to that problem, basically. And there are a lot of times where the problems specifically say, we want you to use some kind of machine learning or AI or something in your solution. So kind of like for you to be in style doing research, you kind of have to have just a little bit of machine learning and AI in your lab. So if you are doing CS and you have a little AI machine learning vision, or you have some experience with that, that would also help you a lot. You would help professors being in style.
I wanted to add one more thing, like I said a lot at the beginning, because all the, I mean, from the presentation tonight, we saw that the main of the presentation is a component of a computational component, right? And it can be orbital mechanics, it can be computational mechanics, you name it. And I think if you're interested in coding, programming, and maybe developing fast algorithm for a specific architecture, that I think is a skill that has a lot of application. And I always think that is a skill that is more and more required, and fewer students have or like. That's my personal view, right? But I think coding, programming, and especially like developing algorithm and taking a step further for a specific architecture so that you can do it. Why? Because you can do it in real time, right? So that becomes the speed and accuracy that become very important when you think about practical application. And you can name it like application you saw tonight, but in the medical field as well. So yeah, I mean, having that type of skill set and also liking that that type of area, I think is a huge plus. Yeah.
Thank you.
So first of all, thank you for all y'all presenting. So this is more of a personal question, but for me, I'm a double major in aerospace engineering and biology. So all of y'all's presentations can relate to me in some form of fashion, from talking about, you know, microbes, propulsion. Like for me, I'm in the Air National Guard and I work on fighter jets. And I really like how that gives me some leg up into aerospace. But I guess my question to you is, so this spring, I have an internship with NASA, and then right after that, I have military training. So I won't be available until the fall. And I wanted to ask y'all, how long are y'all's labs? Like, how long are y'all going to be doing those labs until, if that makes sense?
Till they fire us.
I was going to just say till we're retired. Yeah. That was my first two.
I like both your answer, but that's okay.
No, the labs are that's the research. That's not a class, so they are there.
Okay.
So all the labs should be there as long as the professor is there.
Okay.
So yeah, you whenever you have the bandwidth, definitely reach out to whoever you want to work with.
Okay.
And you know, maybe you will not see the exact same problems. Things evolve with time, but the lab will hopefully still be there.
Awesome. Just wanted to make sure.
Yeah, so I was going to say, so, you know, for the context of the work that we do at the hypersonics lab with Dr. Ahmed, really, I mean, we just moved into a 30,000 square foot facility. RUM wasn't built in a day. And really what we've done at this new facility is set forth the next 2 decades of hypersonic research at UCF. And so there you have it. I mean, 2 decades, right? You have 2 decades to decide if you want to join my lab. For my specific project, the flight experiment, we actively recruit in phases. And so we do so at the start and end of each semester. And so it's a 8-flight series project. So we just finished up the first payload. We're already designing the second payload, and there's 6 more to come. And so even by the time you're a graduate student, there'd still be a place at the lab to continue the research if you start it next fall.
Okay, awesome. Thank you.
Yeah, I don't think it's ever early enough. You know, you can always start to look into a lab, do some background work, like look into the literature. Maybe there are something that you don't know yet, and it will be very useful for doing research in that lab, right? So there is really not, it's never too early. Even if you say, okay, you know, I will be out the next 2 semesters, but maybe you have some times and you can read something in the literature, you can develop coding skills or whatever other skill sets you want to do. And also you can think about the project more and see how you can contribute to the project, what you would do, what you would add to the project. So you're really looking ahead. If you're really interested in this, it's never too early to start, right? You can do it right now, even if then you will join the lab maybe in 2 semesters.
I would definitely love to plan ahead. I'm always planning ahead early, even if that's like 2 semesters early. So that way I have something to look forward to whenever I get back. Cool. Thank you.
So this is more of a specific question for the U-Space lab. I apologize, I don't remember your name. So you were talking about the CubeSats. Roughly, like, how big are they? And on top of that, like, what kind of propulsion system do they use?
Those are two great questions, and I should have brought a CubeSat model with me. Now that you say that, I remembered myself. I should have done that. But satellites come in a zillion different shapes and sizes. A satellite can be larger than a school bus. A satellite can also be smaller than your phone. So it ranges a lot. And a CubeSat, in that word, it means it's based on a cube of 10 centimeters by 10 centimeters by 10 centimeters. So like 4 by 4 by 4 inches-ish. And that's one cube. And normally if you have a satellite that is just one cube, it's not gonna be doing that much. So most of the satellites that are CubeSats are either 3 U's, so 10 by 10 by 30 centimeters, or 6 U's, 10 by 20 by 30 centimeters. And those are the satellites that are most commonly done for CubeSats. And your other question about propulsion, that's a really interesting point because there are a lot of CubeSats that do not have any kind of propulsion. And the ones that do, if you would select one thing that is going to fail in your spacecraft, the most likely one is the propulsion unit. So there is a lot of potential for improving propulsion for spacecraft, especially small spacecraft like CubeSats. You might have heard of the Artemis 1 mission when they launched 12 CubeSats together with that SLS. And last time I checked, I think 7 of them had problems with the propulsion unit. So propulsion for CubeSats is big. It's important and it needs to get solved.
Thank you.
All right, that concludes the research forum. Let's give one last round of applause for all our researchers and for all the wonderful contributions they've made to research. Thank you.